Coding algorithms in different languages. Coding algorithms form the backbone of software development, enabling developers to solve complex problems efficiently. Whether you're optimizing data structures or implementing machine learning models, understanding how algorithms work across various programming languages is essential. The choice of language can significantly impact performance, readability, and maintainability when coding algorithms. This guide explores common algorithms through different programming paradigms, offering insights that help programmers make informed decisions based on their project needs. Understanding algorithm fundamentals across programming paradigms. An algorithm is essentially a set of instructions designed to perform a task or solve a problem. The way these instructions are structured varies widely depending on the programming language used. In procedural languages like C or Pascal, algorithms tend to be expressed linearly with a clear sequence of operations. Functional languages such as Haskell emphasize immutability and recursion, which influences algorithm design fundamentally. Procedural approach focuses on step-by-step execution using functions and variables. Functional style utilizes pure functions without side effects, often leveraging recursion instead of loops. Object-oriented languages like Java introduce encapsulation, making algorithms part of class methods rather than standalone procedures. This shift changes how we organize and reuse code effectively. Each paradigm has its strengths. Choosing one depends largely on factors including team expertise, system requirements, and scalability goals. Implementing sorting algorithms in multiple languages. Sorting algorithms serve as fundamental examples demonstrating differences between programming languages. Implementing quicksort in Python versus JavaScript highlights variations in syntax while maintaining similar logic. Python's list comprehensions simplify sorting implementations but may obscure underlying mechanics compared to explicit loop constructs found in lower-level languages. JavaScript offers flexibility through array.sort method but lacks built-in support for custom comparison functions unless explicitly implemented by developers. Comparing implementations reveals trade-offs between brevity and control over internal workings, crucial considerations during performance-critical applications. Detailed comparison. Quicksort versus merge sort implementation. Quicksort typically outperforms merge sort due to better cache locality even though both have average time complexity O(n) log n. However, merge sort guarantees stable results at the cost of higher memory usage. When translating these sorts into code, functional languages might use pattern matching extensively whereas imperative ones rely heavily on mutable state manipulation techniques. A study comparing runtime benchmarks showed quicksort executed approximately 15% faster than merge sort under identical conditions across several test cases involving large datasets. This difference becomes significant when dealing with real-time systems where milliseconds matter significantly despite theoretical similarities in asymptotic behavior. Data structure manipulations through various languages. Efficient handling of data structures is vital for effective algorithm implementation regardless of chosen language. Stacks, queues, trees, all require careful consideration regarding available libraries and idiomatic approaches within each ecosystem. In statically typed languages like Rust or TypeScript, type safety ensures fewer runtime errors related to improper structure manipulations. Dynamic typing seen in Ruby allows greater flexibility, albeit potentially leading to subtle bugs later. Rust provides powerful iterators along with ownership model features helping manage lifetimes safely, an advantage not present in other environments lacking comparable mechanisms. Leveraging native data types provided by each language helps optimize both speed and resource consumption, aligning closely with hardware capabilities. Algorithmic complexity analysis tools and techniques. Evaluating an algorithm's efficiency involves analyzing time and space complexities mathematically before testing empirically. Big O notation remains standard practice despite being somewhat abstract representation. Tools like profilers offer concrete metrics showing actual execution times varying according to input size. These complement theoretical analysis by highlighting practical limitations affecting performance expectations. For instance, Although insertion sort theoretically runs in O, N superscript 2, profiling shows it performs reasonably well for small arrays due to minimal overhead associated with simple swaps. Combining mathematical evaluation with empirical measurement gives holistic view necessary for making sound engineering choices around algorithm selection. Optimizing performance using language-specific features. Modern programming languages include optimizations tailored towards improving algorithm performances inherently. Understanding these features enables writing highly efficient code suitable for demanding tasks. Golan's concurrency primitives allow parallel processing, easily facilitating multi-threaded computations required by intensive numeric calculations involved in scientific computing scenarios. JavaScript engines employ JIT compilation, enhancing interpreted scripts' execution speeds considerably beyond naive expectations, especially noticeable after warm-up periods. Using appropriate abstractions provided by frameworks reduces boilerplate, allowing focusing efforts solely on core computational aspects crucial for achieving high throughput rates. Practical examples demonstrating cross-language algorithm behavior. To illustrate cross-language behaviors, consider implementing breadth-first search, BFS, traversals on graphs represented differently across ecosystems. JSON format dominates web-based representations, influencing graph construction strategies accordingly. BFS implementation via Python leverages deque from collections module, ensuring optimal popping from front, unlike lists which incur expensive shifts operation every removal. TypeScript enforces strict typing, preventing unexpected mutations, thereby increasing reliability, particularly beneficial during collaborative projects requiring consistent interfaces. These distinctions highlight importance considering toolchain specifics when designing solutions intended to operate consistently across platforms. Choosing the right language based on project requirements. Selecting suitable language hinges upon evaluating specific project constraints alongside desired outcomes. High-performance computing demands low-latency operations achievable only certain specialized tools provide access to. Web applications benefit immensely from client-side scripting capabilities offered exclusively by JS/TS Stack, enabling interactive experiences unattainable otherwise without server round trips. Maintainability concerns drive preference toward languages possessing strong community backing, providing extensive documentation, reducing friction faced newcomers joining existing teams mid-project lifecycle. Ultimately, decision must balance immediate needs against long-term sustainability goals, ensuring solution evolves gracefully, accommodating future expansion requirements organically. Conclusion: coding algorithms across diverse languages showcases vast landscape available. Modern developer communities engage daily. Recognizing distinctions among paradigms enhances ability, crafting robust, scalable solutions tailored precisely meeting application demands. By mastering fundamentals coupled with awareness platform nuances, practitioners gain power selecting optimal combinations, realizing fullest potential any given scenario presents uniquely.